Right. Welcome everybody to a webinar from the American Nuclear Society's Risk-Informed Performance-Based Principles and Policy Committee, RP3C we call it. My name is Prasad Kadambi and I'm chair of RP3C. The purpose of RP3C is to help modernize ANS standards. Modernization has come to mean that risk-informed and performance-based methods are employed to overcome the difficulties that we all know about with purely deterministic and prescriptive methods. We have been calling these methods RIPV approaches. The Nuclear Energy Innovation and Modernization Act has included RIPV in statute, as it were. There is a lot of guidance available on RIPV approaches, but most people have not had reason to become familiar with the guidance because the conventional approaches still dominate most things that we do, including standards development. Right now, ANS can be considered as a knowledge center for RIPV methods, if only through the library of videos that we have developed on the RP3C web page of the ANS website. I hope all of you will take advantage of that. Today's Community of Practice webinar is going to talk about one of the instances where modernization of standards has in fact worked very well. And I hope you will see how much better standards can be if we employ these modern methods. The community of practice sessions are held on the last Friday of every month, except next month, because the last Friday comes right after Thanksgiving, it will be held on November 19th. So if you wish, you can mark that down on your calendar. Today's presenter is Kent Welter, one of the people who helped us all get started with this community of practice. He's with NuScale, and he's going to tell us how a modern version of a light water reactor design standard has been helping his company. Kent?
All right, thank you very much, Prasad, and thank you, Pat, for hosting a presentation today. As Prasad said, my name is Kent Welter. I'm a chief engineer of testing analysis here at NuScale, about 20 years experience in the nuclear industry, 13 of that at NuScale, helping to commercialize our small modular light water reactor technology, and then about 6 years before that, the Office of Research at the Nuclear Regulatory Commission, supporting new and advanced reactor design certification reviews. The title of my talk, I'll give sort of a update on ANS-30.3 for those who aren't familiar, which is a standard under ballot right now, entitled Advanced Light Water Reactor Risk-Informed Performance Design. And then kind of pick one of the sections of that standard, section 11, that provides guidance on performance-based decision-making and how at NuScale we've implemented some of those requirements and guidance from ANS-30.3 into our business practices and design process. Acknowledgement and disclaimer from the Department of Energy. This material is based upon work supported by the DOE under this award number, and nothing that I say in this presentation, the government makes no warranty express or implied or assumes any legal liability. The accuracy or completeness or usefulness, I like that, of the information. I find it, hopefully it will be useful. Real brief outline terms and definitions. I think I only have one term. A little bit of background, talk about some of the performance-based decision-making requirements in ANS-30.3 and then an example implementation of that. And I don't have a lot of slides today. Only have about a dozen or so slides of content, and we'll use those sort of as a talking points as I go through the presentation. But if anybody, I encourage, communities of practice is like a lot of knowledge sharing, and so I definitely would be interested in taking questions and or comments about your experience in this area as well throughout the presentation, because I think we have plenty of time. Don't have a whole bunch of slides. Right, performance-based from ANS glossary of terms, an approach to design or regulation that relies upon the desired measurable results or performance outcomes based on objective criteria, key, rather than prescriptive process, technique, or procedure. A little background on ANS-30.3. Since 2018, so almost 5 years now, NewScale has been supporting or chairing myself the development of ANS-30.3. A little bit of background is why we decided to support this, why NewScale pays for my time and considers development of this standard and other standards to be important to our success as a company. Is really to, when we were, NewScale started about 13 years ago to commercialize an advanced LWR technology. And when we were preparing for our design certification application, which we submitted in, it was 2016, and we got approval in 2019, we were looking to modernize and use risk information in our design process early, using early results from the PRA, setting performance objectives and using systems engineering best practices to design our reactor. At the time when we were looking around for standards, really the best thing that we could find at the time was ANS-30.3, which was a risk-informed performance-based standard for gas reactors. But at the same time, it was written fairly technology neutral. And so there was a lot of, I think, good techniques and guidance in that standard. And we evaluated it, and we took a lot of those concepts to Nuclear Regulatory Commission at the time during pre-application and presented some of those ideas about using the concepts of 53.1, of a technology neutral standard for risk informing in the NewScale design and licensing process. At the time, we got a fairly warm reception, I guess, in terms of conceptually using the approaches. This was back in 2012 or 2013, so almost 10 years ago. But at the time, it didn't seem that the NRC was ready for a light water reactor to apply those concepts directly. Because again, they were kind of technology neutral, more in the advanced reactor, gas reactor kind of space, and some of the terms and some of the concepts of using frequency consequence curves and just but they weren't quite sure how to get ready for that as they were developing a design specific review standard for light water reactors. So there was a gap there, but they were supportive, but they said it was going to take work for us to demonstrate how we were going to do that. So there was a fair amount of burden on us to do that. We decided at that time, since to not use 53.1 in our design process, but we still used the risk information from the PRA quite extensively in supporting a design certification, and we followed the standard review plan, and I think it was very successful on both NewScale and NRC side to complete that review, on schedule, and get the design certified. And we did use risk information and performance best techniques, but when we came back and we said there really wasn't a standard that kind of closed that gap between, the, say, technology neutral, quote unquote, advanced non-light water reactor standard and NewScale. So we proposed to write something that was a little bit, use a lot of the techniques and concepts from 53.1, but maybe had terminology and sort of some practices from the light water reactor community that would be a little bit more familiar to industry and the NRC. So long story short, on that first bullet, that was why NuScale decided to propose this and has supported it ever since. ANS-30.3 went for ballot. And just not for NuScale. So we also believe, and we got that this can be a useful standard to any advanced LWR designer. So we are just guinea pigs, so to speak. So ANS-30.3 went for ballot this year after about 3-4 years of development with about 100 comments. The working group went through and addressed all those comments, and we just resubmitted the draft standard for to the Light Water Reactor Consensus Committee for review and consideration. Previous to that ballot, official ballot, we had about 2,000 public review comments that we addressed, and we've gone through essentially two main revisions. One main revision after the public review, and then a second main revision after the ballot. So we got, I think, a lot of really good constructive comments and questions about the standard, and I think it definitely has improved through that commenting process. All right, so it is currently back for review at the Consensus Committee. I would like to recognize a lot of effort from the working group, significant contributions from David Blanchard, Don Doobie, Prasad Kandalbi, Paul Sicard, Cindy Williams, Patrick White. It's been a real collaborative effort, and we've all spent quite a great deal of time developing the content and responding to the comments. So thank you very much. The contents of the standard have about a dozen sections. It talks about the nuclear design process in general to kind of set the stage. It's a process-based standard, so it doesn't. When we get into the next section, talks about defining a process for identifying safety requirements and functions, and using systems engineering best practices. But it doesn't go into specifying what the safety requirements, other than a very high level, should be. It specifies 3 basic safety requirements that are consistent with IEA approach for safety, but beyond that, it's up to the responsibility of the designer to go through a systematic process for identifying safety requirements, safety functions through iterative and recursive design. The standard then goes into talking about process for licensing basis event identification, both from a deterministic and probabilistic perspective, so risk informed. Provides guidance on design basis safety analysis, probabilistic risk assessment, classification and categorization of system structures and components, systematic approach for implementing defense in depth principles and evaluating the adequacy of defense in depth, and then performance-based decision making. And that last one, performance-based decision making, is the section we're going to talk about today. So within ANS 30.3, and again, I'd like to recognize the significant contribution from our host today, Prasad Kandalbi, for helping to draft and this section of the standard. It has a lot of good guidance. I picked out some of the requirements that I think are important and that have set the stage for the implementation of performance-based decision-making at NuScale. So the first one is performance-based safety objectives shall be used to support decision-making related to design and evaluation of plant systems and components. Now, in a systems engineering best practice, objectives are typically transformed into specific requirements in the design that must be met. And I'll talk about that a little bit, and how we do that, and how those requirements are flowed down to the design process. Second bullet is the decision-making process during the design development shall be formal and evidence-based in order to allow for explicit treatment and consideration of risk insights into the design. The next one is the decision-making process shall also incorporate decision analysis that evaluates decisions against specific performance safety goals. And this talks to having specific decision criteria that's written down and agreed upon, that when decisions or changes in the design, or not changes or modifications to design come up for consideration, that they are evaluated against specific criteria. Also have qualitative criteria, but this is an express direction to evaluate them against quantitative criteria as well. And the process itself shall have the following characteristics: objective criteria to assess performance based on risk insights, deterministic analyses and/or performance history, quantitative and qualitative criteria. This is important for transparency and repeatability of decisions. And new Reg BR 0303 provides additional guidance on a decision-making process. The ANS-30.3, I'd say, goes into a high-level prescriptive requirements on the process, but then it references new Reg BR 0303 for more specific guidance. Important in the decision-making process, especially when considering systematic defense in depth, is a recognition in the decision-making process of different levels and types of defense in depth when considering alternatives, including evaluation of safety margins and their trade-offs on plant capital and operation costs versus risk reduction. When using risk insights, it's also very important to evaluate and understand the sources of uncertainty and how they're treated in the PRA results, and how those uncertainties can affect the decision itself. So sensitivity analysis, understanding, sensitivity analysis is a very powerful tool for helping us understand the uncertainties and the assumptions in the PRA. I don't see any hands raised or anything in the chat yet, so I will press on. I guess I'll pause there because I'm about to just kind of get into the new scale implementation. If there's any sort of questions on ANS-30.3. All right.
Yeah, carry on.
Thank you, Prasad. So, new scale implementation. This is a little oversimplified because we have various internal standards and procedures that govern this work, but I tried to simplify it for communication. So we talked about the need for establishing effective performance-based decision-making, establishing safety performance objectives. Again, systems engineering best practices, objectives, criteria, requirements, they are different terms, but they can kind of be synonymous for today's talk. So at NewScale, we have what's called a plant technical requirements document for every one of our plant baselines. In that plant technical requirements document, I'll show in a little bit, we establish high-level performance objectives, not just safety, but there is an entire section on safety, performance, and defense in depth. Step two is when we in the design process and the requirements engineering process, we look to allocate those high-level performance objectives to the various products and or systems through iterative and recursive design. So we take some of these high-level goals. A straightforward goal would be internal events core damage frequency goal of less than or equal to, say, 1e⁻⁷. That's a high-level goal. And then another one might be something to do with shutdown margin. Another one might be backup power supply. So we take some of these high or reliability, say, of the system, or a reliability of providing power, which then you could allocate to a backup power supply. So we look and we analyze these high-level performance objectives, and through that design requirements engineering process, we work to assign them to the appropriate systems. In some cases, there is no system assignment and they are maintained at that high plant level, but if it makes sense, we do work to assign and allocate those. Step 3, and we do that through, I'm sorry, on the left here, we do that through what we call parameters and limits reports. So at the next level in design, we have parameters and limits reports that set the design constraints, and those are informed by those high-level performance objectives. Step 3 is identifying, as they're going through iterative and recursive design, defining what's called key performance indicators, KPIs. And that's based on looking at this, say, collection of high-level safety performance objectives in the PTRD, the design constraints that are put into the parameters limits reports, and as they're starting to flow down in system equipment specifications. And the KPIs are a combination of technical and project performance indicators. They say, all right, I've got this design and these constraints, and we've got, X amount of years to get it done, and here's an X amount of money to get it done. What are those key quantitative sort of indicators related to performance that we should be tracking through our decision-making process? So obviously there's a lot of engineering judgment that goes into selection of those, and I'll give an example of the ones that we've selected for our latest version of the NuScale plant. Now, once we've selected those KPIs, it's important to establish decision thresholds. And this helps with, IMPO safety trait on decision-making is to, in practice, as best as we can to put the decision-making at the lowest level in the organization as possible, so the folks who are closest to the problem or the system are empowered to make those decisions. So I'll talk about the importance of setting decision-making thresholds and how we use modern engineering change control process to fast-track most of our engineering decisions based upon these decision thresholds, so the work can progress and the folks that are closest to the work can be empowered to make those decisions and only escalate when needed. And so, and then that's step 5 is monitoring the effectiveness of those KPIs and the decision-making boards and make adjustments as needed. All right. Digging in a little bit to those, the process I outlined at a high level. Technical requirements documents, we sort of call these level 0 documents. They're fundamental documents for each one of our plant baselines. They define the top level product requirements and allocate top level requirements for NuScale plant configurations. We actually have a separate document that serves as a primary input. Systems engineering rely on systems engineering best practices to identify and elicit stakeholder needs, goals, and objectives, and we do that through something called a plant concept document, or PCD. So for each one of our major design configurations, we have a plant concept document, and that's where we get input from the customers, our executive team, and the engineering team, the product teams, the supply chain, and we put together in a document the concept for that product, because it might be different a little bit if a concept is in a different country or in a slight variation if it's in a different part of the U.S. There might be transportation requirements that need to be considered and so forth. So we start with that plant concept document, and then we, as a design team, we look at it and we create this companion design report or design requirement specification to essentially understand and interpret what the customer wants, stakeholders want, and then we put that into a spec at the highest level that goes into the design process, and that's how it gets started. So requirements and goals and objectives there are in the PTRD. It's a collection of requirements and goals. So it's mostly requirements, mostly shall statements, but then there are definitely some, you would say, stretch goals. It says this is a requirement and a limit, but it'd be great if you're this much above that limit, as an example. These are some, from a safety perspective, these are just a few I pulled in no particular order from one of our PTRDs for the NuScale plant. First one is the plant shall be capable of cooling a NuScale power module, as our reactor, without external makeup water to replace ultimate heat sink boil off for a minimum of 30 days. So that's a very specific requirement related to cooling the reactor, and no makeup to our ultimate heat sink for a specific amount of time. So that's a quantitative safety performance objective. And there's other ones here. There's one that says after a design basis event, the plant shall provide automated actions that place and maintain the power module passively cooled with K effective less than 1 for at least 72 hours. So we've designed the reactor to not require any operator action for the first 72 hours. It's a passive plant sort of design and licensing precedent, but we've put that specifically as a design requirement so that we can ensure that it's met and it's allocated to the appropriate systems as we go through the design process. The one on thermal margin for the fuel, 5% or greater than SAFTLs. The plant CDF for internal beyond design basis events during full power shall be less than 1 to the -7. Conditional containment failure probability shall be less than or equal to 0.1. So this is a collection of, I would say, design basis safety performance objectives and some beyond design basis safety performance objectives. But that's the first step, is making sure that's established at the high level in a plant technical requirements document, are these types of performance objectives. Now we get into sort of the next level where we identify parameters and limits. So instead of requirements statements, we sort of jump to parameters and limits, and they're directly derived from the PTRD requirements, and they provide key discipline interface design parameters for all of the engineering disciplines and product lines for that plant baseline. We split our products into the NuScale power module, which is the reactor and the containment vessel and associated passive safety systems. We also have ones for the core and the fuel, and the reason why is because certain customers might feature one a slightly different fuel cycle, right? And so, but in the same physical configuration of the reactor modules. So we separate that to allow for different product lines to have different versions and reusability. We have our buildings in a separate set of parameters and limits reports. There are some customers that want slightly different configurations of buildings in different countries, so we split those out. The INC systems we split out into parameters and limits as well. Refueling and remote handling, because it's a little bit different in the NuScale design, and then balance of site, which is turbine building, switchgear, all that kind of stuff. So we split these at the next level down, and we identify these key parameters and limits that drive the design process or constrain the design process within these product areas. Example here is table 212 from the reactor core and fuel parameters and limits reports. Talks about the different modes of operation, 1, 2, 3, 4, and 5, and cold shutdown. And we have limits for boron and RCS temperature for those various modes. I had to remove those there because they're proprietary. But essentially that establishes design constraints for that product area. And what we do then is in the next step, so what we did now is we have this collection of documents that have a lot of design parameters, limits, and constraints. Then that third step is, well, those will be pushed into requirement specs and designed to. But then from a decision-making perspective, is there a subset of key parameters that we should be managing as a development team and a product team to support decision-making as we go through that process? And so that's that. In systems engineering, that falls under what's called technical measurement. Technical measurement is they're essentially activities to provide stakeholders, whether that's internal stakeholders like the engineering and product teams or project teams, or external stakeholders like customers or regulators, insights into the progress and the development of the system or plant as it's going through that design development process. And those insights really help make better decisions through the life cycle of the process. Now they can change, like they definitely, as you're going through big phases of a design process, the key performance indicators, that list might change a little bit. And the values certainly might change a little bit, and the thresholds might change. But the key is to evaluate all your design constraints as soon as possible, early in the design process, look for a subset of KPIs and formalize those into a decision-making process. The four main types of technical measures, I won't necessarily get into these, are called measures of effectiveness, measures of performance, technical performance measures, and key performance parameters. Long story short, KPIs are just a subset of all those four main categories of technical measures. At NuScale, currently, for our US 460 product line, US 460 megawatt electric product line, a 6-pack plant, our key performance indicators, not a complete list, and I don't have the specific values or thresholds on the side here. Need to remove those from for being proprietary. But I wanted to show that the nature of the KPIs that we track on a weekly basis. Core thermal power is a not necessarily an obvious one, but we're going through a power up right now, and so we have a target for that, and we definitely are tracking that and have decision thresholds. So if there's a change coming in that might say, hey, it's going to go up or down in power by a megawatt or whatever, we've got a decision threshold that might kick that up to a higher level of management review. We have the unit gross output that impacts on like steam conditions. That's an important aspect of design. House loads, that's also important as we're sizing equipment, sizing the feed water pumps, all the other various equipment that needs electricity. That house load just kind of slowly creeps up, and then it kind of decreases the total output. And so we want to manage that and track that so that the total power plant output meets the customer requirement. There's cost in here: fixed O&M, operation maintenance, variable O&M, and plant overnight cost. We have thresholds associated with that. Now we start to get into some more safety aspects, emergency planning, those sides. The NuScale reactor has a design requirement of a 0 EPZ plume exposure pathway size. And so we track that. A protected area size from a security perspective, construction duration, minimum licensed operators, plant staff, containment peak pressure margin. So that's one we also track. Conditional containment failure probability. We noticed, or I presented earlier on plant technical requirements, we had a requirement that it should be less than or equal to 0.1. And so if we're going through any design modifications or tweaks that potentially could impact that, we'll calculate that and see how we compare against it. And that'll be input into the decision process. Dose margin to Part 100 limits and fuel thermal margin. So it's not a complete list, but it provides an example of a collection of, I would say, business, costs, schedule, and safety and risk performance objectives that we implement at NuScale. Pause there and see if so far. Doesn't seem like it. All right, we'll carry on. All right, enterprise change assessment and integrated decision making. So at NuScale, I would say in the last several years, we've implemented what's called a CM2 implementation of configuration management. That's a brand name, I believe, from a company called ITX. And it's a company that provides training guides on enterprise change management. So change management across the entire enterprise, not just say in design, but supply chain, finance, that kind of an aspect. And there's a real value proposition associated with managing change across the enterprise using a consistent process to enable repeatability and transparency of decisions. We have implemented the CM2 approach for our design process and our engineering change control process. It's outlined here, and not necessarily planning to go through every aspect of the NuScale engineering change control process, just to identify a couple key features. On the left here, anyone can submit an engineering change request. It goes through a review process. What's interesting is we have what's called change leaders. These change leaders are trained individuals that can quickly identify a couple things about a change, and it's really to identify, is this a change that is routine, that I can use a fast track criteria, and essentially air traffic controllers send it to this group. That's sort of their first sort of series of questions they evaluate. And if it can, then it goes boom, and the change gets implemented, bypasses a change review board, and it gets implemented as quickly as practical, following our procedures and practices. If that change is not fast-tracked, or it's not sure if it's fast-tracked, then the change leader has an ability to expand the scope of the impact evaluation, bringing additional subject matter experts to evaluate, do a second evaluation if they can fast-track or not. Sometimes they say, yep, you can fast-track it, goes back. Otherwise, they expand the impact evaluation to evaluate the impacts of the proposed change. Those impact evaluations then formally get presented to a change review board. And in that process of evaluating those potential impacts and even that fast track, they look at those KPIs as one of, they look at other things as well, but every time they evaluate every ECR against those KPIs from the previous slide. And that really helps to identify, I guess, initially the fast track criteria and decision threshold. So back up a little bit, the change board went through a review of these lists of KPIs and had looked at the values and said, all right, if it's going to change by this much, or collection of these are going to change by this much, we want to review that. If not, we can fast track it. And what that does is that helps us process changes effectively, but still have the necessary oversight that we need for product development. The goal for fast tracking is that 80% plus of engineering changes are fast tracked. I had them pull the data a couple weeks ago as I was preparing for this, and we're actually doing quite well here at NuScale and are above that goal. So from that perspective, we think it's working pretty well. And then also, because our culture is a conservative bias, every so often the change leaders will be saying, well, we're not quite sure if we're meeting some of these thresholds. This is like, we're kind of on the fence if this is fast track or not, and they'll come to the board for guidance. And so that's also an important indicator that we're evaluating if those thresholds make sense and making any changes as needed as we go through the process. So a couple of key messages. One, it's important to have a formal, obviously, change control process, decision-making process for product design. And it's also super important to have clear performance objectives and decision thresholds. It's really effective for making timely decisions that are transparent and repeatable. So the engineering change board is not the only sort of decision-making board at NuScale that looks at performance objectives from a safety and risk perspective. We have what's called the Design Reliability Assurance Program, or DRAP for short. It's a regulatory requirement and important aspect of the design process. Essentially, it ensures that the plant is designed and constructed in a manner that is consistent with the key risk insights and assumptions from the PRA and other deterministic methodologies. And so it's a expert panel that primarily looks initially at helping to categorize system functions based on safety and risk. So the system designers will go through a procedure and a process for categorizing the safety or risk significance of a system function. That goes to a independent expert panel, which actually I chair, and we evaluate those recommendations from the system designers on the categorization of system function, safety related or not, risk significant or not. Then that goes, we approve those system function reports. It goes back through a process of the design process, and then further on down, we get a summary report of the subsequent classification of the system and components that are risk significant, and a DRAP report, and those come back. So it's an expert panel that presides over review of every system function and functionality of the plant, and then eventually the risk significant systems and components and structures that get identified and classified. And so it has a fairly important influence on the design. So it was very important when we updated this process recently to instill performance-based decision-making techniques. And I think we actually presented on our SSC classification process in a previous RP3C community of practice a couple months ago. So if you want more details on our implementation, I think you can find it on the RPC3 website, community practice website. So anyway, intro aside, so we took ANS-30.3 guidance from section 11 on performance-based decision-making and put that into our procedures. And specifically, it's almost copied and pasted. Yeah, copy and pasted those process requirements from ANS-30.3 into our DRAP procedure. So as we're going through as a DRAP expert panel, as we're evaluating system functionality, as we're looking at the safety and risk, we're utilizing to some extent these key performance indicators and all the performance-based decision-making techniques that are described in ANS-30.3. There's an important companion section of our DRAP procedure that talks about defense and depth adequacy, and that's really where the expert panel spends their deliberations, is talking about defense and depth and risk significance and following these performance-based techniques, performance-based decision analysis techniques, excuse me. Okay, wrapping up. So summary and conclusions. ANS-30.3, I think, biased opinion for sure, provides good requirements and guidance for advanced LWR designers like NewScale for implementation of performance-based decision-making. It has, a LWR flavor, right, in terms of terminology and some of the techniques. So it's not, say, as technology neutral as other standards or guidance out there. But there was a reason for that that I think I talked about earlier, and a need to fill that gap. NewScale has implemented a couple key aspects of 30.3 to support effective performance-based decisions. We, through our design process, systems engineering process, we establish high-level safety objectives, PTRD, allocate those to SSCs, through iterative and recursive design, through parameters and limits reports and system functional specifications and design specs. We establish key performance indicators with decision thresholds, including, very importantly, fast track criteria. And we utilize those KPIs in our various decision processes and our boards for reactor design, the key ones being engineering change control and our DRAP expert panel. And we've seen a marked improvement in the timeliness and effectiveness of decisions utilizing these performance-based techniques, specifically KPIs. Our metric for effectiveness, one of them, are the number of ECRs that are being able to fast track. And we are actually at about 87% of them right now. So that's exceeding our 80-20 goal or rule. So With that, that's all I have for today. Thank you very much for listening. And if there's any questions or comments, I'd be happy to take them.
Kent, I want to thank you for this presentation. I think we do have a number of people representing some advanced reactor projects that are ongoing right now. I'd like from you is sort of some indication of how important you feel it is for you as a company to support standards development, because what I'd really like to see is more of these advanced reactor projects, allocate some resource to standards development and, support for the standards efforts at ANS, I hope, but also other standards developing organizations. So just a pitch for consensus standards.
Sure. Early on, we recognized the need because the NuScale designs, advanced LWR, it's based on decades of proven technology. It's the same fuel. Essentially, it's in the current fleet. It's a little bit different. It's half height. It's a pressurized light water reactors, natural circulation. So it's not super advanced, but it's packaged a little differently. And maybe some conditions are a little bit different, and the way that we use risk insights is a little bit different than the operating fleet, for example. So when we looked at trying to apply modern approaches of systems engineering and risk-informed performance-based design, we found a lack of standards. And we know, we think we, well, let me back up. And that was just one area. The other area was for specific ASME components. Others are like SC wall construction. So these things are sort of modern approaches. It wasn't just because we were so different from what was already approved. It's like there are better ways of doing things, right? And we would like to have a consensus, an industry consensus, and also endorsement to some extent from the regulator on new and better ways of designing and building nuclear reactors. And so I think since our culture is innovation, we really saw the value of supporting standards that would modernize the nuclear industry, frankly. And we spent a lot of time and effort trying to do that in a lot of different areas. So yeah, it's super important not just to get standards approved if they don't exist because you're using a different material, but it's also important to look ahead at better ways of doing business and support those standards as well.
And a key is, as you mentioned, submitting the standard once it's done for regulatory endorsement, because by that process, the standard becomes part of the regulatory framework, because consensus standards are by law required to be, given sort of priority over government-issued, requirements, promulgated requirements. So, I'd say that's another reason for companies to support standards development. So there's a question in the chat. Ken, perhaps you can look at it and answer it.
Sure. Having gone through it, do you think this performance-based approach is ultimately faster, more effective than the traditional prescriptive approach? Yes, I absolutely. We've gone through our design we certified recently in 2019 was called our US 600 design. It's a 150 megawatt thermal reactor with 12 reactors in one building. And we spent considerable time and effort going through that. Because of just customer needs, we uprated the reactor and reconfigured it. So we got another chance to sort of upgrade the reactor a little bit and reconfigure it. And we implemented several new processes because we thought continuous improvement. We went through it a couple times, and this new way of doing business is much more effective. It's the processing of ECRs is streamlined, but it's also the ability with these change layers to scale the impact evaluations and rapidly respond to larger potential changes, and evaluate those impacts quickly to cost, schedule, safety, and risk, get that to a board for review and approval while the other work is continuing on. It's frankly, having lived through all of it, it's night and day difference. I very much recommend it.
Kevin,
I don't know if that answers your question. Mm-hmm.
Steve Stam over here. Can you hear me?
Yeah, go ahead, Steve.
Yeah, a question that based on listening to you, and actually I knew this anyway, but you are in an ideal position to provide the standards committee with thoughts on new standards that we could develop that would support ongoing new reactor development. And so I would just ask that you consider that, and basically, if you have some thoughts, that you pass them along.
Sure. Thank you, Steve. Will do.
Thank you.
Let's see. I don't see any other hands up. Questions. I guess.
Gary asked one here.
Oh, okay. I'm sorry.
I think the question is, how do you apply risk-informed, performance-based approaches when considering regulatory guide requirements that may be applicable to our design? I'm maybe interpreting that is there is a body in the U.S. of regulatory guides for light water reactors that may not consider these new modern approaches to risk inform. Some of them might, some of them not. And how do we go through that process? Is that correct, Gary? Or maybe you could clarify your question if you can come off mute.
Gary, are you able to use the microphone to?
No.
Okay.
He says yes.
Yeah, go ahead.
There's no. I think in general, we're preparing for another round of submittals with the Nuclear Regulatory Commission in the next year, submitting a standard design approval application for our uprated reactor and six module configuration plant. And we're looking at, the extent to which to apply some of these concepts from ANS-30.3. I really don't think it's inconsistent with the regulatory guidance that the NRC has put out. What we're evaluating, I think, is the measure of risk informing, and we're still going through that. And that can be sort of almost event by event or system by system, component by component. So there's a measure of risk informing a system or a plant or a decision through the design process. And I think in general, the framework and the NRC is very receptive to risk-informed concepts, but I think it does depend on the situation. And there is some precedence for risk-informing in certain areas and not. So we're carefully going through that in our development of our application and trying to figure out specifically how much to risk-inform and in what areas. So, but we definitely will be risk-informing like we did in our design certification. Sort of a very generic answer.
Next question from Rob Hayes. You can read that in the chat. He also put it in the chat.
Sure. You're in the chat. If folks aren't able to see it, it says, the question is from Rob Hayes. Do you have a formal protocol for maintaining continuity of knowledge? The KPI process is critically dependent on cognizant engineers over all effective systems being available for implementing any change. Well, so yes, I mean, there's what's important with that is identification of a key role in our CM2 process called the change leader. And that change leader has formal training and an understanding of that, those KPIs. And yeah, the identification and training of a core group of change leaders, and then we have folks rotate in and out of that, and we have formal training associated with that. That's how we maintain understanding of those KPIs and how they potentially impact is through formal training and knowledge management of the change leader core. Really good question.
So Kent, I think we are almost out of time. I want to thank you very much for this presentation. And, you know, I appreciate everybody who has participated, and look forward to seeing you at the next Community of Practice session, which will be on November 19th. And it will be delivered by X Energy, also an advanced reactor development project. So thank you all very much. Pat, back to you.